So we're talking about actors. What's that? Oh, yeah. Sorry, go ahead.
All right, welcome everyone. Let me make sure I have this thing on. It's been a long day, long week. So this is a community-run event. As you know, it's like, if it wasn't for the sponsors, we couldn't make this event happen at the kind of prices we do. So I'd like to thank everyone for attending, but I also need to thank our sponsor for this room, which is OpenSUSE. There's a few little things in the back, kind of gives you some hints on some of the OpenSUSE stuff. So OpenSUSE is, I got something called Open Build Services. So I'm going to read you a little part of that. So OpenSUSE's Open Build Services offers powerful team and project collaboration features for forking of packages and merge requests. It's called OBS for, Open Build Services. It builds Debian, RPM, and TGZ for ARM, V5, V6, V7, and x86, and more for 28 Linux distributions. That's a lot of distributions. It pull code directly from Git or SVN and build each source package from a fresh VM with OpenSUSE OBS. Again, I would like to thank OpenSUSE for sponsoring this event. And with that, I give you your main movie tonight, right?
Yeah. Thanks. Nice. So we're talking about actors today, and specifically how they're totally unrelated to movies. But with the subtitle, that was the title that was supposed to get you guys in here. But the subtitle of this talk is that we're coupling our architectures. We're moving from fiction, which is how we think we build software, to reality, which is coupling them with physics. So I work for VictorOps. We do on-call management software. So basically, when your infrastructure goes down in the middle of the night and somebody's got to get up to fix it, we're the ones that are doing that. So we have a really nice real-time processing flow where we take alerts in and turn them into incidents and then go out and page people. So we're built on top of Scala. We use the Play framework, and Akka is a JVM actor framework that we're using. And that's primarily what we're going to be talking about during this presentation. I'm on the Twitters down there, Boulder Dan H, if you have any questions now, after, whenever. So the motivation for this conversation and this presentation actually began about 4 months ago when we decided that the current way that we were processing alerts was getting really bogged down. So we had a very traditional multi-processing system all backed by a single database. And there was a tremendous number of queries that would occur every time that we processed an alert. And because we think about our alerts as sharding really nicely across companies, as in no two companies' alerts should ever really contend with each other, we thought this system has got to be much more scalable. And so we decided to rewrite it as an event source system. And if you're ever interested in what we're talking about here, event sourcing is a great way to implement really highly scalable systems, but that's much more advanced than what we're going to be talking about. So a couple of the things that came out of this, and it is kind of motivation for what I was thinking about the whole time I was writing this talk, is that scaling up is not a sustainable practice, right? I mean, I almost wish that scaling up wasn't even a word, because that phrase is a contradiction in terms, right? Scaling is usually adding capacity by getting wider, right? So what people talk about when they're scaling out. And scaling up is just adding big iron onto things. And of course, your system gets faster if you add more CPU or more RAM. But that's not really an interesting property of a system. It's also difficult to scale out to lots and lots of processes. And the reason that is because our languages and frameworks are really geared towards running on a single box. And we're going to talk about this because there's an answer to all of this. And it really is embracing the concurrency that's happening inside of our systems. And I believe that designing and constructing software that embraces concurrency is a way to build systems that can scale out. So a brief digression here. I want to talk a little bit about the difference between concurrency and parallelism. In a lot of contexts, these two words are used interchangeably, and that's perfectly fine. But in distributed systems, there's a very specific way that we can talk about these that makes the reason for why we're building software clear. So the distinction, concurrency, is all about independent processing. So we can actually write concurrent software on a single processor, right? This happens all the time. You have concurrency with a processor trying to execute instructions and a keyboard trying to interrupt that. Those are two concurrent things occurring. Even if I only have one processor, it's still concurrent. Whereas parallelism is all about things happening simultaneously. So concurrency is about designing software, and parallelism is the implementation of the software. We also often talk about asynchronous things when we're talking about concurrency. So a brief example, if I were to start a company called Transmogrify Incorporated, and I turn lead into gold, seems like a pretty good business model. And so my business model in today's world is represented by this little red arrow. And so these lead things come in and they get turned into these little gold statues. So a way to think about this in concurrency is, what if I broke this into two separate steps? Now, that pink blob is supposed to be gold, but I'm not very good at Photoshop, so you have to, just look at the way that it's supposed to be set up. But basically, if I break this up into two separate processes, one half is the golder and maybe the other half is the guy that does shaping, and now I can build a pipeline, right? And this is just standard good software, right? You break things up into functions. And so in our case, we're taking lead, we're turning it into a gold color, and then we're turning it into that little statue guy. And I could flip it around so that now it's turning into the statue, and then it's turning into gold. And as long as I have separated these into independent processes, this all works. And you might ask, well, isn't this more work to do? And the answer is yes, it's more work to do multiple steps. And so it's probably a little bit slower, but at runtime or at implementation, I can now add scale to it. So I can add more things that do things, right? Maybe it's processors, maybe it's RAM, but the point is that by adding design here, I can now scale my solution. And this is the kind of scalability that's interesting in architecture. So concurrency leads to parallelism. Good concurrent designs can be implemented in a parallel way, and parallelism is what scales. When I was doing research for this talk, I found a lot of really interesting parallels between what we're doing in software and what hardware is doing under the covers. So here was one conversation that an Intel engineer was talking about when they were talking about adding additional microprocessors and cores into our systems. So the biggest problem that we're running into is data contention when we add parallelism. And if data contention doesn't make sense, you can either think of it at the top, some kind of traffic jam, or a little bit closer to computers. It's just a whole bunch of computations all trying to use a single resource. And it might look like a database, but it really could be any kind of shared memory. It could be anything that many computations want to share, and we can't have them all using at the same time. And a lot of what we do in concurrent systems is to control the way that we attach these resources. So I want to take some of the big frameworks out there and split them along an axis and talk about them in relation to each other. And so I'm loosely calling these pieces of software monolithic versus distributed. And this is not to say that you can't write distributed software in Rails and that you can't build giant monolithic things in Finagle. But in general, this software lends itself towards building certain kinds of applications. And so Rails and LAMP I broadly classify as being monolithic. And Finagle and Erlang/OTP I would broadly consider to be distributed. And there's actually a more fundamental decision that these two frameworks make that we're going to start off here and then get to. So a monolithic architecture very often looks like this. You've got a whole bunch of web users. They all try to access a web process, and that web process calls back to a database. And when you look at this, and when people typically write their Ruby processes running inside of Unicorn, they don't think about concurrency. They just say, I've got my single-threaded application, and I take the data in, and I spit it out to the database. But of course, if you look at this entire system, there is concurrency happening. Right? All of these people are not hitting the server at the exact same time. I've got 4 web processes. I've got a database that might have row-level locking on it so that different processes can be checking out data at the same time. The problem, as I see it, is that the concurrency is very hidden. It's a latent concurrency when people don't think about it. And so the concurrency ends up being unplanned. And it relies on a subset of the system to handle concurrency. For the most part, in the architecture I just showed, it's typically at the database level. It's the only part of the system that understands that there are multiple threads of control. And the problem is that it's therefore unplanned, and you don't get the benefits of scaling. The alternative, as I was pointing out, is a more distributed architecture. So this is a pretty standard, completely made up and maybe a little bit difficult to see, but a pretty standard fan-out architecture where the web processes are now hitting those processes below, and then those are hitting services, and those services have workers. And so there is still contention going on here, surely. You know, there are a bunch of people trying to use service E at the same time. There are workers. But it's more planned. The concurrency is everywhere. When we look at the entire system, we can see that there is concurrency happening. And so there is a huge reduction in the contention of the entire system because there's more pieces to it. And so this type of architecture is much more parallelizable. It's much more scalable. It also has better resource density in our data centers, so we're utilizing our hardware quite a bit more. You've got, all those multi-core processors, the big $12,000 servers you're buying, they're all being used. And we get really fine-grained control over our scaling. So if any part of this system you determined was running slowly, because of course we measure before we change, you can go back in and add more of them because you've built concurrency from the ground up. And so I believe that planning for concurrent systems is really key to building sustainable architectures. And I think that there are some ways that we can be doing that better. But there's also a fundamental choice when you start going down this path. And that is that I have to choose a way to control that concurrency. Because when I start adding it, all this non-determinism comes with concurrency. And so figuring out a way to make sure that I can still reason about my systems is really key. And so if we think about the way the concurrency control works, you can break it up into 2 different worlds. It's shared data and not shared data. So obviously those are 2 flip sides of the same coin. We also often call not shared data message passing is another way, and a lot of these are really just duals of each other. And so let's go back and recharacterize the monoliths in the distributed system, because I would contend that the real choice that Rails is making is shared data concurrency. That's what a database is. And the choice that Erlang and Finagle and microservices is making is message passing. They're sending messages around to change state. They're not relying on one central storage device. And when you talk about shared data concurrency, just to get very clear about this, we use these types of words, right? So shared data is really, we're talking about primarily shared memory, but even a shared network resource like a database. And so you talk about locks and semaphores, and when you go to a lower level, memory barriers and compare and swaps and STM. And if you Google multi-threading and concurrency on Stack Overflow, you get 65,000 questions of people saying, why doesn't this stuff work? And the problem is that the primitives that were given by language designers are just really tricky to use. So they give us all these primitives to use, but they're really hard to use correctly. Does anyone recognize this pattern in Java? Does anyone think this is intuitively clear that this is thread safe? This is kind of crazy, right? I mean, you're checking for null in two different places. You're synchronizing when are variables, volatile. Has anyone read the JSR 133 and just come away and gone, I have no idea what this means? I mean, you have to be Doug Lee in order to understand this stuff.
I like that Matt Doug Lee.
Nice. So this is another quotation from Intel trying to build asynchronous chips. Have you guys ever thought about the fact that when people say that I have a 4 gigahertz chip, that you have billions of transistors all working at the exact same time? Like, that's crazy. Who would build software where the entire software package has a strict clock that it's running against? So Intel is trying to build asynchronous chips too, because it takes 22% of a CPU's power just to maintain its clock. And so, but they have the exact same problem, that their tooling isn't there. They can't build asynchronous chips right now for many reasons. It's a huge jump in complexity, but the performance gains would be massive if we could get rid of that. I mean, it's only 4 billion instructions per second, but it could be faster. So actors are an example of a shared message, of a message passing framework. And on the JVM, which is I prefer because I really like Scala, there is an actor framework called Akka. It's made by the same guys who built Scala. It's built by the lead software architect who used to work on this cache thing called Terracotta. It was just massive JVMs. And he decided that trying to build memory spaces across machines was madness, and that there had to be a simpler way, and that the actor model was that way. So actors are a reasonably old concept. They first came about in 1973. They were being used for artificial intelligence work by a guy named Carl Hewitt. And they're a really fundamental concept. So they have really grand visions of themselves. Actors are a fundamental unit of computation. They actually compete with the Turing model as a different way to think about how we can build computation. And so they embody 3 different properties. The first one is that actors can create other actors. And the second one is that they can send messages to each other, and that's how they communicate and do processing. And the third one is that they can store information for the next message that they receive. So their state is kind of for the next message that they get, not for the current message. They're not reassigning variables strictly. They're storing information for the next message, and that'll become clear in a second. From these theories, we can build axioms on top of them, because actors actually implement actors, and it goes all the way down. Even their mailboxes are supposed to be implemented in actors. But we can build some axioms on top of that to make it a lot more clear. So actors have a mailbox, and they only process a single message at a time. So that's really, really fundamental. That's what's really cool about them when we talk about concurrent systems. So in a lot of ways, an actor is similar to an object, except instead of having a reference to a piece of memory, we actually have an address to an actor, and that actor could be anywhere. And then, so actors really, they model concurrency and distribution. And those 2 key concepts make them really good for building big systems. So my subtitle of this talk was Coupling Your Architecture to Physics. And I thought this was such a cool insight that Hewitt had. And that is this idea that So this is where we diverge from the Turing model of computation. So a really simple example here, this actor is going to send himself the stop message, right? He sends it out, and as soon as he sends that message, or she, we start sending increment messages to ourselves. And what's cool about actors is that we don't define the way that these channels work. And so the final state of this actor can actually be anything. It can be 0, 1, 2, 3, or 4, or 1, 2, or 3, because that stop message goes out into the ether and comes back to me, and I have no expectation on when it will get to me, if it will ever get to me. And this fundamental property of actors allows us to model distribution really, really well. And I just thought that was such a cool example, because you can't do that with a Turing machine.
You mean sort of a quantum actor? It's in those 4 states simultaneously? Is that what we're saying?
It's not in all those 4 states simultaneously. When it receives that stop message, it could have received 0 or more of its increment messages. They're asynchronous.
All 3 plus 1 and the stop are asynchronous.
Yeah. And it's asynchronous, and it is completely an unbounded amount of non-determinism. So I think that's pretty cool, because it facilitates a lot of the way that we use actors. They are at the implementation level, but they are not fundamentally in what actors are. Like it happens to be that we have contiguous memory and we implement them with queues, but there's nothing intrinsic to an actor saying that I have to get those messages in the same order that I sent them.
Oh, right, yeah.
So let's jump into code. Has anyone ever seen Scala code? Nice. So Scala is like this crazy functional, strongly typed language. But the cool thing is we can ignore the types, or it will infer the types, which makes it pretty okay to demo because I don't have these big massive types all around. So this is like the simplest actor I could think of. It's a counting actor. Line 2 there, I've got a variable that keeps track of the count. And I receive messages on line 5, and people can get messages from me. Really, really simple. But what you'll notice isn't here is there's no locking. I've just got this really simple variable. It's not even an atomic integer. It's just an integer, and I increment it. And because of those axioms and the theoretical stuff we were talking about earlier, you know that this code is thread safe. It will only ever process one message at a time, given a good implementation. It's just intrinsic. It's just, that is what the actor gives you. It relies on the fact that this actor class has been implemented correctly, but your code is not supposed to worry about that. So if it is only ever processing one increment message at a time, then I will never have 2 threads of control that are both trying to increment a message.
But the receive method you have on here is not overriding, so it's just your local receive method, right?
Yeah, that's the way that Scala works. This doesn't have to be an override because there was no definition above it.
So it was an abstract definition above it?
It was an abstract, yeah. It doesn't have to be overridden by default. So here's another way that actually encapsulates that idea that I was trying to explain. It's complicated to explain, but actors can store the state for the next message they receive, and this is how you can implement that in Akka. So instead of my receive block being this partial function, my receive block is actually calling a function that returns a function, and I'm passing my initial base state of 0. So every actor begins with a state of 0, and when I receive the increment message, I call this special method called become, and then I call the next function again and give it the next state. So when the next increment message comes in, it will have the state from this count variable in a function. So this is another way of expressing this actor without using reassignment. And so, yeah.
Might you call that a monad?
I don't know. Do you think it is it?
A function that returns a function and there's no shared state. No.
I don't know if we have it's not really a wrapper around anything. But it is a way to do stuff functionally because there's no variables going on here. And in fact in Erlang there are no variables, so this is kind of how you implement everything. So maybe, giving an example that has a little bit less contrivedness, but only barely, I could actually implement bank accounts as actors. And so in this case, this first line here is a constructor, and I'm passing in the name of the person who owns the bank account. And I might give more realistic messages like credit and debit. Maybe you can ask for your balance, ideally. And people can even send in this little string here that says, who are you? And I'll return the name of the current actor. And I could model my entire bank as an actor. So this is the idea that an actor can actually create other actors. So if I say that I have a new bank called the HSBC Bank, and it's FDIC insured, and when I send the add account message to this actor, it will create another actor. And so the state of the running system is all these running actors. And so now I can begin to talk to these actors concurrently, these sub-actors, because they all have their own address. So a program using actors, the first thing that we have on line 2 is that actors belong to a system. They have to have some place where they live. And then I create an instance of an actor, one of those counter actors, right below that. And then I send it the increment message. That's what that exclamation point is. We'll talk about that. And then I ask it, I want to get its current state now. So I use that question operator, and that will return me its current state. And in Scala, we have this construct called a future. And so the question mark operator will return the future of a value. And so at some point in the future, we'll have a value. And that's what this guy down here below does, is that when the result is redeemed, it will print it out. So all of this stuff is non-blocking. It's all asynchronous. It can all happen concurrently.
So the callback from the increment is that on success?
Is this result. So I ask the counter actor to give me its current state, and the question mark guy returns me a future of when that will be redeemed.
And when that future actually arrives, it's then the on success?
Yeah. Yeah.
So if I had another line of code after the result on success that printed a different line, it's likely that would print first, and then the...
Yes, exactly. Yes.
So that's purely a callback function. That's what I was saying, that result.on success.
Yes. Yeah, this part of it is the callback function. Yep. So there's a key abstraction in here that I kind of briefly talked about when I said that they were like objects, and that is that every actor has an address, right? So this is how you talk to an actor, is that you get a reference to his address, and that's where you send messages to. And what's really cool about that address is that it doesn't tell us anything about where that actor is. So when I instantiate this actor, we all know from looking at this code that this actor is running inside of the JVM, the same memory space that this program is running inside of. Or at least I'm telling you that that's the way it works. But without changing this portion of my code at all, I could actually move this actor to another data center or to another process. And this part of the code would never change because the sending mechanism is always static. So actor refs give us this property called location transparency. that no matter where the actor is deployed, you'll always access them through a single address. And that allows us to make decisions about how we deploy our software really, really late in the game. You know, I would say it's kind of a runtime or config time decision. And that has really cool properties because without changing this code, I could add 10 of these counters, and they would all look the same. And it would be completely transparent to this guy. And so if my increment method were really, really slow for some reason, and I wanted to add a big pool of actors that handles that, this code would never know that. It would be completely transparent. So it's kind of like that idea of how nice it is to have a DNS name that I can stick a load balancer behind. Because to the outside world, we don't know that there's 500 servers serving my application. And that's what gives us really good scaling properties. So the sending messages I was talking about, we've got the exclamation point, and we say that as tell is the name of that operator. And tell is an asynchronous method that takes any type and returns nothing. That's what unit is in Scala. It's kind of like void in other languages. So all of those methods are just sending and then moving on to the next line of code. That's what we mean by asynchronous code, right? But I can still ask for information using the ask method, which is the question mark. So I send a GET request to this counter method, and I get back a future of that value. And that's just a Scalaism. But basically what it means is that the actors are now talking to each other. So the ask method is actually implemented by creating an actor, having that actor send a message to whoever you were trying to send to, and then that guy responds. And then that actor that you just created temporarily redeems the future and gives you that value. So that's an example of actors implementing actors. So actors are really, really good at concurrency because primarily because there's no synchronization or none that we have to worry about, because it's fundamental to the way that actors are built, that they'll never process multiple messages at a time. All the communication between actors is completely asynchronous. That whole coupling to physics thing is what allows us to say that the actors can start off in the same JVM and then they can exist somewhere else, because we don't define the amount of time that occurs when we send a message. And it allows us to make late binding deployment decisions. They're also extremely lightweight. At least on the JVM, they're on the order of bytes in memory, because it's really the implementation is just a queue in a class. Like, that's pretty lightweight in most languages. So in a sense, in the very purest sense that we talk about microservices being less than 100 lines of code, they do one thing, they have a REST endpoint. Actors are microservices. And so when you model your behavior in systems, you can get really, really granular and build these really tiny actors that do one thing. They do one thing well. They have a very small memory footprint, and they're very, very small. Now, we were talking primarily about actors, but there are other ways to build message passing concurrency into our systems. And one of the big ones is not a duel of actors, but there are a lot of interesting comparisons between the two, and that's communicating sequential processes. So this is what Go is built on top, or one of the metaphors that Go gives us. In addition to Go routines, they also have channels, and channels are an implementation of CSP. CSP is from the 70s as well. I think that's when all the best computer science work happened. The key distinction between the two, I've been harping over and over on the fact that these actors, when they talk to each other, the way that they communicate is a very ill-defined, amorphous thing. But in CSP, that channel is the fundamental unit. The input and output of the way that processes talk to each other is really fundamental in CSP. The communication along that channel is synchronous instead of asynchronous. So if one thread of control tries to send a message to another thread of control and the other guy isn't ready, it will actually block the first thread, and that has nice properties. One of the big problems people have with actors is that the way that to implement back pressure is quite tricky. You can often end up with one actor with a really, really big mailbox just chugging through work, whereas all the other actors are just sending him data willy-nilly. And so CSP has a very natural implementation of back pressure. There are also channels are anonymous in CSP, and actors are named in the actor framework. That was a distinction. I'm not a huge CSP guy, but there was enough comparisons that I thought it was worthwhile talking about. It's also really popular right now. So some of the other message passing frameworks that you might consider, streams, like the reactive project that everyone's talking about right now, is a really good choice. That actually that came out of the desire to have stream processing with back pressure. So reactive Java is, yeah.
Are any of those three for C++ at all? Or are they all
For C++?
Yeah.
I don't know.
Or COBOL.
Reactive is actually a standard that people are implementing, so I wouldn't be surprised if there was a C++ version. I wouldn't be surprised if there's an actor model for C++. So reactive Java, there's one built on top of actors from the Akka team. Streams is a really cool idea. We've actually been looking at that a lot because back pressure is something that we deal with that makes me nervous. Data flow is this really old concept from a programming language called Oz. I always include it just to be thorough, but it basically makes asynchronous code look synchronous. There's an implementation in Scala using macros, but I don't know how much traction that gets, or I don't know what its influence, but it seems pretty cool. And then CPS, continuation passing style, it's like what Node does to do concurrency control. It's not strictly message passing, but if you use it correctly and you're not closing over your shared data, then it can be message passing-ish. And CPS should not be confused with CSP, which is an unfortunate naming thing. So wrapping up, I believe that concurrency is inevitable. And, you know, you guys might say that there's a naturalist fallacy here, that because it's inevitable, should we really embrace it? And maybe not, but I think it has really good properties when you do embrace the concurrency that's already happening. I mean, I did some of the research for this, and I was looking from the lowest level, from the CPU up, how much concurrency is happening in our system. And it's just mind-bending, the amount of non-determinism at all levels of software that's going on, from the CPU and the way that it handles interrupts all the way up to having networks. I mean, basically, it's everywhere. And if you're not building control for concurrency in, then I think you're just ignoring how computers work. And maybe that's fine if you want to build algebras and you're building mathematical models, but in systems that have to remain up and in systems that have to embrace the fact that computers crash, I think embracing how they work is really key to getting performance and scalability. And so using tools that helps us to build good concurrent architecture, I think, is key. I would suggest that message passing is a really good way to go for that, because shared message or shared data is kind of a cluster. And if you do all these things, I think you'll scale. That's the key. So, are there any questions?
Yeah, you mentioned there were some other competing paradigms for this. You mentioned communicating sequential processes like Go.
Mm-hmm.
I don't know very much of anything about that.
Okay.
And I guess if you could go into that a little bit. And also, would you consider STM? be another approach to that?
To message passing?
Well, I'm not sure. No, to the concurrency issue.
Oh. I know.
I wasn't sure whether you were highlighting that these were all message passing ones. You had communicating sequential process and actors, and then it just occurred to me, in addition to those two, I assume those are for concurrency.
Yes.
Concurrency, there would also be STM as additional.
Yeah.
Another approach, right?
Yeah, and I think I generally lump STM into kind of the shared data model of the world. It does certainly a very good job. You know, STM and CAS really give you nice tools to do shared data. But I think moving towards message passing is a better way to go. The other tools that help you, these are all message passing frameworks. So the Reactive Manifesto gave us streams. Tony Hoare in the 70s gave us CSP, and Go was an implementation of CSP, and data flow and continuations.
What would be the actor best practices for dealing with failure? So you kind of send a message, and then the other actor fails. You do it. Some sort of broker that would handle a retry or things like that.
Right.
Your stack traces are going to be all wonky, aren't they?
Yes. Oh, absolutely. So the question is twofold. One is how do actors deal with failure, and the other one is don't your stack traces get all wonky. And so the second one is absolutely. As soon as we leave a single thread, our stack traces are gone, right? Because we're leaving the stack. And maybe that's a bad thing, but I think you can get better instrumentation. Less around, I mean, we rely on the stack traces to see problems that are going on, but there are other solutions like the Dapper paper that help us to instrument distributed systems in a way like stack traces used to do for us. And then the first part of that question was how do actors deal with failure? And a lot of that falls on building tools on top of actors. So by default, actors implement at most once delivery. They send the message and hope that it gets there. So kind of like UDP does. If you need to switch mechanics to something like at least once delivery, or God forbid you think you can implement once and only once delivery, that all is implemented. It can be used. You can use actors. You know, you can send messages to them, create a transaction ID, send that transaction ID to another actor, force them to acknowledge it back. But a lot of that, you know, what they say is that you don't want the framework to implement at least once and only once delivery, because you don't care that somebody got your message. What you care about is if they did something with it. So what a framework can give us is that this packet got from here to there, but that's not interesting. And so it really is a function of your business layer to decide that something was received correctly and acknowledged back. And so for the most part, it falls on the people building the system to determine what is an acknowledgeable thing and then write code that retries it if it fails. It also depends a lot on who cares about failure, which side of the world. Yeah.
And just to add on to what you were saying, these models usually have this idea of a supervisor process.
Mm-hmm.
That when this actor that you sent something to has crashed, and there's a supervisor that, you know, you're sort of encouraged to let stuff crash in your language, in your
Mm-hmm.
design. But and the supervisor process can optionally throw away the messages in the mailbox or not. Am I right about
Mm-hmm.
that?
Absolutely. So that's almost.
The issue of pending messages in the mailbox comes up when you have a crash.
Also,
Yeah, absolutely.
pattern is to send a message and then expect a response, and after a certain timeout, maybe just send it again. And if you get the first response back or the second response back, you just ignore whatever comes in after that. And
Yep.
The second, like, who cares? I timed out. So it's a pretty simple pattern to work around.
Mm-hmm.
Are timeouts primitive?
Are they fundamental to the way that actors work? They're like in that question mark in the ask method that takes a timeout, so that if the future hasn't been redeemed after some period of time, then it throws an exception and you get a failed future. But you could.
Retry and
Yep. Mhm. Absolutely. Anything else? Yeah. Yeah. I worked with Evan. Oh. So I think is Puma better than I don't know the answer to that question. I kind of stopped doing Ruby a couple of years ago, but
what other languages other than Erlang and Scala do you know have an actor model?
so the question is, how many other languages have actor models? I would be surprised if you couldn't find a framework for most high-level languages. I know there are a couple on Java.
Well, since Akka works in the JVM, all the JVM languages.
There's definitely some trickiness when it comes to running actor frameworks on top of the JVM. There's a lot of angry blog posts about how it's a really terrible idea. And that is based primarily around the fact that in Java, our threads are mapped to native threads. And so in a language like Erlang, where they've written their own virtual machine and they have green threads, they can say that every actor has its own thread, and that's totally kosher. And on the JVM, if you had 1 million actors and each one had its own thread, your system would fall over. So you end up having to be very careful about not blocking threads in the JVM. So that's one of the caveats with doing something like Akka. But
Well, you shouldn't be trying to do that anyway, right?
I don't know. I mean, if you're blocking, but the thread scheduler can know that and then take that thread out of the rotation, I think that's perfectly okay. But if you block a thread and then the system's thread scheduler can't do anything with you, then that gets more tricky. Yeah.
So, I think it'd be interesting if you could talk a little bit about some of the real-world applications where CSP is used versus actor-based models are used, particularly in the context of peer-to-peer networks, for example, or other large-scale systems.
Okay. So the question is about real-world uses of CSP versus actors. From what I understand about CSP, it doesn't model distribution in quite the same way that actors do. I mean, actors are all about creating systems that span the globe. Like, they're almost fundamentally about that. And I believe CSP is more about concurrency control in a single virtual machine or a single machine. So it depends. If you're building big distributed systems, it seems to me that actors are maybe a better model. I know CSP has a lot more foundation in process calculi and the lambda calculus and really making mathematical models around computation. And again, actors disagree that that's a good way to do things.
Other real-world examples
Of actors or I mean, Erlang builds all their telecommunications using actors. We have processing using actors. There's some online gaming company that represents every single one of their users as an actor. Could be implemented or uses. Oh, sure. Riak? Yeah. There's a bunch of Erlang software out there. That's not completely contrived, like mine are.
My company's about to open source something. It's called.
Here, let me give you the mic.
Oh, very cool.
Can you hear me? I can't hear me. Okay, good. My company is working with Akka and
That's working. Yeah, I can hear it.
My company is working on an open source tool where
Test. No.
called CDG. It's a test runner that'll run parallel tests. So you can have a cluster of machines running like say Selenium tests, which Selenium opens up a web browser and clickies on your app. So a pretty big app, so it takes all night to run it on a single machine, but it takes 10 minutes to run all the tests using actors. So that's kind of a great. So that's a good example. We'll be releasing that sometime this year. We're going to call it, well, right now it's called CDG, but we probably can't call it that when we release it. So
Nice.
it is, but technically it has an open source license, but it isn't publicly available. So. Yeah, it'll be on GitHub at some point.
Under what company?
Sorry. My company is Commission Junction of Advertising. Oh, thanks.
Cool. Well, I have a couple of references. Don't bother trying to learn those now. They'll be up when I publish the slides. They'll be all up there. But otherwise, thanks a lot.
Thank you.
Yeah.